So the next talk is going to be given by Saleo on yield sampling lower bounds by separator.
Let's see, is this working? All right, good. Hi, everyone. This is a paper by Emanuele Viola. I'm not Emanuele Viola. I guess the reason Emanuele, he unfortunately wasn't able to make it to the conference, I guess the reason he asked me is that I was his PhD advisor about 20 years ago. He was my first student. So if you take away one thing from this talk, for those students here, in 20 years you can ask your advisor to give a talk for you. All right, so this talk is about sampling lower bounds. So to contrast with the usual kind of lower bounds that we study in complexity theory, we normally often study lower bounds for computing functions. But sampling lower bounds are, which kind of came up also in Rahul's talk, is lower bounds for sampling distributions. So you feed the algorithm uniform random bits, and then its goal is to produce a sample from some particular distribution. There's been about a decade of work on this that Emanuele has been one of the people kind of initiating and pushing with some really interesting connections, some connections to randomness extraction, extracting from so-called sampleable distributions, which won't come up in this talk. And the results of this paper of Emanuele's are relevant also. This sampling lower bounds are also relevant to lower bounds for data structure problems, which we'll touch on. So we want unconditional lower bounds. So against restricted models of computation, the model of computation that Emanuele is looking at in this is our forests. So our algorithm, again, is given uniformly random input. You can think of this as uniformly random bits, or more generally, uniformly random sequence of words from some little w bit string. So capital W is 2 to the little w, and you have capital L, those inputs. And then it operates as a forest, so each output cell is computed by a W-ary tree. Think of this as a generalization of a decision tree of depth q that gets in each node gets to query one of the input cells. So this is basically a time queue algorithm in the cell probe model. And you have one tree for each of the outputs, so that's why he's calling it the model of forest. And again, if you prefer, you can just think of decision trees, so you can think of the word size as 1. If you like. Okay, and one motivation is again for data structure lower bounds. So the cell probe model is a standard model used for understanding the efficiency of data structures. So think of X here as the data structure. So by preprocessing your data, you store it in this vector X. And think of this y1 to ym as being the answers to little m different queries that you might make on that data structure. So that's the connection. And one thing that might seem a little weird is, for this data structure connection, is that here we're considering the case where the input here x is uniformly at random. Why would your data structure be uniformly at random? Well, the kinds of data structures that this gives lower bounds for are what are called succinct data structures, where you take your data and you store it in a data structure that's only slightly bigger than the information theoretic optimum, right? So if I'm storing k bits, I store it in k plus certainly little o of k, and often k plus some very tiny amount bits in my data structure. And so this way, if I take uniformly random data and I store it in a succinct data structure, what I'll have here is not necessarily uniform, but it will be not too far from uniform. And you'll see why the lower bounds here then might still be relevant to that those problems. Okay, so again, there's been this line of work on lower bounds for sampling, and there's been a lot of work by Emanuele on showing hardness of sampling certain distributions for AC0 samplers. So instead of forests, AC0. And AC0 is more powerful than forest by the usual way that AC0 can simulate like decision trees, sort of just generalizing that to these cell probes. But these kinds of lower bounds are for somewhat complicated distributions. Things related to sampling code words in an error-correcting code, for example, or things related to randomness extractors, these kind of pseudo-random distributions. And so we do have lower bounds for forests, but limitation is, one, since those lower bounds are coming from lower bounds for AC0, they won't give you a separation between AC0 samplers and forest samplers, which we would like to have. We do know separations for computing functions between AC0 and forests or decision trees. And also, we would like lower bounds for simpler distributions than the lower bounds we have for AC0. And in particular, some of these distributions, again, are very basic data structure problems. Okay, and so that's what this work gives, the new lower bounds for sampling by forests that separate AC0 and forest samplers. Also gives a hierarchy for forest samplers. If you have more depth, more queries, you can sample more distributions. And again, they apply to some simple distributions. The data, and which give data structure lower bounds. These aren't new data structure lower bounds, but they follow as kind of easy corollary. So it's a new way of proving these data structure lower bounds. And the main kind of technical tool in proving the lower bounds is what Emanuele calls the separator. You can restrict your inputs so that the output distribution is close to being pairwise independent. And we'll see that in more detail. Okay, so let's kind of get to the concrete statement of results. The first one is for sampling the rank distribution. So here this is the distribution you want to sample from. So imagine you have a uniformly random string of m bits, and then look at the following sequence. The first bit, the sum of the first two bits, the sum of the first three bits. So this cumulative sums. So that gives some distribution on integers to the m, integers from 0 to m to the m. So that's the distribution we want to sample from. So again, relevance to data structures. Imagine you have a data structure that is storing these prefix sums in some way that you can efficiently recover. Your data is an m-bit string, and it's stored in some data structure, and you want to be able to efficiently recover any prefix sum is the relevant data structure problem. And so you've stored it in this data structure, W to the L, a very succinct data structure that's using just barely more than little m bits. And now your forest, again, can recover any of these prefix sums. And what Emanuele proves is that if you try to do so, your statistical distance from the right distribution, so it's using this notation function of a set that's used. This set is also representing the uniform distribution of the set. The statistical distance, total variation distance, will be very close to 1. 1 minus exponentially small, or 1 minus actually 2 to the minus little m, divided by word size to the number of queries. Okay, and this turns out to be a tight lower bound. And again, since we're getting these lower bounds where the statistical distance is very, very close to 1, you have to be extremely far. That's why it gives like interesting lower bounds for these succinct data structures. Because again, if you encode uniformly random data in a data structure that has only slightly more length than the information theoretic minimum, then the distribution is, has some non-negligible kind of intersection with the uniform distribution on your data structures. And so, anyway, that's just a high level, right? So you get these lower bounds for succinct data structures and reprove lower bounds for ranked data structures. I think tight lower bounds for ranked data structures. All right, so this already gives some kind of a separation between AC0 and forest samplers. It turns out rank can be sampled by quasi-polynomial size AC0. It's an interesting open question whether it can be sampled by polynomial size AC0. So you can do some translation, like just change parameters to get a separation between AC0 and forest samplers, but it won't be quite as strong a lower bound as you'd like, and so we'll look at another function that gives a bigger separation. And so that's for this predecessor distribution. So now again, we start out with uniformly random x, and now we again get a sequence of numbers out, but they're not the prefix sums. It's this saying for each output coordinate, the ith output coordinate tells you the largest value of j, largest coordinate of your input x, that's assigned to 1. That's less than or equal to I. So the kind of predecessor that's assigned 1. Here it turns out that predecessor x is no longer, we don't think of x as uniformly random anymore. It turns out that's easy to sample. I haven't worked out why. Maybe it's a good exercise by forests. So instead, Emanuele considers some other distribution h, which is a bit harder, and shows that for this distribution h, again, we have a very same kind of lower bound as last time. And this distribution can be sampled in polynomial size AC0, and so you get this separation between forest and AC0 samplers. And this is also what gives a sampling hierarchy, that if you increase depth so depth order q, you can sample distributions that can't be sampled by depth q. Okay, and so now kind of getting a little bit into the techniques. Also, by the way, stop me if anything I'm saying doesn't make sense, because it could be that I just misunderstood something. Okay, so this separator main technical technique in the lower bounds. So again, we have our forest f and some distribution that it's trying to sample from. And we want, we suppose for contradiction that it does sample at a non-trivial statistical distance, like less than 1 minus epsilon from the distribution S. And again, think of S as both a set and a distribution. So it's a set and the uniform distribution on that set. Then there's a large set D. So we can restrict from the uniform distribution on W to the L to some large subset of it, such that the output distribution is still close to S, though we'll capture that in a different sense than statistical distance that we'll make precise in a moment. And second, that for most pairs ij of outputs, they will be close to independent from each other. So that's the close to pairwise independent. So what is item 1? Item 1 is that the support on the restriction D, on this restriction of the domain, will be contained in the support of S, which isn't guaranteed by the statistical distance condition. And second, the min entropy, so basically this is capturing the size of, the min entropy of the output will be not too far from the min entropy of the uniform distribution on S, so, or the distribution S. So just differing by an order log 1 over epsilon. Okay, and then there's some, quantitatively, it's important to compare this entropy loss to the number of pairs of output words that are almost independent. But in the talk, it doesn't kind of get into that. But to make the actual proof work, you have to care about the quantitative relationship between these. And all right, so how does this give the lower bounds? Well, the thing to observe is that in these rank distribution and predecessor distribution, the pairs of coordinates are very much not independent from each other. So in the rank distribution, remember, it's cumulative sums. So that's always a monotone increasing sequence. So things can't be kind of close to independent because, Fj always has to be, the output of Fj always has to be bigger than or equal to the output of Fi. If j is bigger than I. And similarly, predecessor, I guess, is also a monotone increasing distribution. So that's how we get the lower bounds. All right, so how is this the separator from the separator? So how is the separator proven? I feel like I've missed. Okay. Given the separator, how do we, no, this is the high-level proof idea of the separator. All right, so which we'll go in a little bit more detail in a moment. The idea is that if you have, if things are, how could the outputs of the forest be dependent? Well, intuitively that should happen if they are intersecting in the queries they ask. These are again cell probe algorithms, and so they access the input by making queries. And at least when our input was uniformly at random, the only way you can create correlations is to be intersecting on the queries that you ask. But if that happens, then what we want to do is say, okay, well, we'll kind of fix the values of the intersecting queries, which will be kind of restricting our domain, but it will have the benefit of reducing the depth of the forest. Because if each query, right, it makes each of the trees makes one query at each kind of level of depth. So, and whenever you fix queries, you've restricted the depth, and you kind of iterate. It apparently gets fairly technical to carry this out, but that's the kind of high-level plan. Okay, so to just in a little bit more detail, we didn't talk there really about too much about condition 1. So in condition 1, one constraint was that the support of f of d on this restricted set is close to is contained in the support of S, and so the first step is basically just to get condition 1 to hold while keeping the statistical, or at least, yeah, the first step is just to get condition 1 to hold, which you can just do generically from the fact that the statistical distance is 1 minus epsilon. All right, and so then the work is really to get item 2. And so item 2, Emanuele uses this this lemma from his previous paper, GSV, S is Chaltiel. I should have looked up the authors. From that paper, there's a lemma. Whenever you have a forest like this, all right, so now we've already done some restriction to some set D, which may not be a product distribution anymore. So we started with uniform. We've done some restriction. It's not a product distribution. But this fixed set lemma says we can, if this has high entropy, you can restrict it to a distribution further that looks like, that's indistinguishable from a product distribution to small depth trees. So that's the next step. We look at this D prime. It looks like a product distribution to small depth trees. Now, if it were truly a product distribution, then what we said earlier is true, that the only way correlations can be created is by intersecting queries. Right? If the input cells are independent, you can only create correlations in the output if two of your outputs query a common cell. But now it turns out that it suffices also on D prime, which is not truly a product distribution, because it's indistinguishable from a product distribution by our computational model, namely these forests. Okay, and so that's what happens now. So if two of the Fi and Fj, two of our output cells, are not close to independent on D prime, then you can actually argue that they must often ask common queries, often over the distribution, the input distribution, and you can do this restriction, fix the value of those queries to reduce the depth and not lose too much entropy, and you iterate. Okay, so to summarize, in this paper, Emanuele has given new lower bounds for sampling by forests that separate AC0 and forest samplers, give a hierarchy theorem for forest samplers, and apply for these very simple distributions, this rank distribution, predecessor distribution, which yield new proofs of data structure lower bounds as a kind of immediate corollary. And main technical tools, this separator, to restrict the inputs to forests so that the output distributions are close to pairwise independent. All right, that's all.
Questions?
Sally, could you put it a little bit more formal, the definition of what is almost independent?
I'm afraid not. We could look together at the paper and try to figure it out.
Close to something, you know.
Yeah, I didn't look up how Emanuele formally defined the almost pairwise independent. Sorry. Yeah.
More questions? All right, before you get an even more technical question, let's think.